So far, every method we've built finds one root at a time. But a polynomial of degree n has n roots, and some of them can hide off the real number line, where Newton and the secant cannot follow. This episode is about finding them all efficiently and in the right order. Two old tools, sharpened, Horner's method, and deflation. Welcome back to Numerical Methods, Episode 5. Zeros of polynomials, Horner's method, and deflation. First, the promise we are working toward. Every polynomial of degree n with n at least 1 has at least one root, possibly complex. Apply that repeatedly, and a degree n polynomial has exactly n roots in the complex plane, counting multiplicity. One word of care, because it trips people up. Here complex means a number in the complex plane, and that includes the reals, which are just complex numbers with zero imaginary part. So the theorem promises n roots in all. Some may sit on the real line, some genuinely off it. Take our quartic, degree 4, so 4 roots. 2 of them are real, and 2 are a complex conjugate pair, off the real axis entirely. Newton and the secant can chase the two real roots. The complex pair needs a different idea, which is exactly where this two-part story is heading. To find a real root, we run Newton's method, and Horner's tableau hands Newton both p and p prime at every step. Newton's rule: the next guess is the current one, minus p over p prime. We will do the synthetic division on the left and keep a running record on the right. Start the first guess at 2.5. Coefficients across the top, 2.5 on the left. Bring down the 1. 1 times 2.5 is 2.5 under minus 3. Add minus 0.5. Times 2.5 minus 1.25. Add minus 0.25. Again minus 0.625. Add 0.375. And 0.9375. Add 1.9375. The remainder is p at 2.5, that is 1.9375. Now the second pass on the quotient for the slope. 1 times 2.5, 2.5, add 2 times 2.5, 5, add 4.75 and 11.875, add 12.25. That remainder is p prime at 2.5, that is 12.25. Feed both into Newton. 2.5 minus 1.9375 over 12.25 gives 2.34184. That's our first row and our next guess. Second iteration, same table, now at 2.34184. I'll fill it in at once. The two remainders give p about 0.37 and p prime about 7.7. Newton again. 2.34184 minus 0.37318 over 7.69828 is 2.29336, row 2. From here it's just more of the same, so let the table do the talking. Each step roughly doubles the correct digits and p collapses towards 0. Row 3, row 4, row 5, and there's our first real root, about 2.288795. We have one root. Deflation factors it out, so we never have to chase it again. If x hat 1 is a root, then x minus x hat 1 divides p exactly, leaving a quotient q1 of 1 lower degree. Here is p degree 4. Synthetic division reads straight off its coefficients 1 minus 3, 1, 1, 1, dividing by the root x hat 1. Divide, and the bottom row is the quotient, the cubic q1. Degree 4 has dropped to 3. Now recurse. Find the next root of q1 the very same way, using Newton, with Horner supplying the values. Seed at 1.5. In each step, evaluate q1 and its slope, and then you see the correction shrinks fast. It settles on the second real root, x hat 2, about 1.389391. Deflate again. Q1's coefficients 1, minus 0.711, minus 0.628, minus 0.437 go into a new division, this time by x hat 2. The remainder is 0 as it must be, and the quotient is R quadratic Q2. Are Q2's roots real or complex? Its discriminant is b squared minus 4ac. Negative. So Q2 has no real roots. Its pair is a complex conjugate pair. Degree 4 to 3 to 2, and that last pair is episode 6. So what are the roots of that leftover quadratic? Check the discriminant. B squared minus 4ac comes out negative. Negative discriminant means no real roots. The two remaining zeros are a complex conjugate pair. Minus 0.339093 plus or minus 0.446630 iota. These roots are not present on the real axis. So these two roots are the ones that Newton and secant could never reach from real guesses. Here the quadratic formula finishes the job. But if a leftover factor were a cubic or a higher with complex roots, you will be needing a method that finds them directly. And that method is Müller's method, which will be discussed in next episode. One honest warning before you trust deflation completely. Every deflated root is only approximate. So the quotient Q1 carries a small error, and the next root you pull from it inherits that error, which grows as you keep deflating. Concretely, if we kept the first root to only 3 digits and deflated, the second root drifts to 1.388933, which is wrong in the fourth decimal. The fix is simple and worth remembering. Use deflation only to get close, then polish each root with a few Newton steps on the original polynomial, but not on the deflated one. Here's the whole plan in one frame. Horner evaluates the polynomial and its derivatives cheaply, in one pass each. Newton rides on top of it to find real roots fast. Deflation shrinks the problem after every root, and whatever complex factor is left over is handed to a direct method. Cheap evaluation, divide and conquer, and an honest handoff. That's how you find every root of a polynomial. A little fine print before the exercises. First, deflation error accumulates. For stability, peel the smallest magnitude roots first and always polish on the original polynomial. Secondly, Horner gives the derivative for free, so there's no excuse to approximate it. So use the exact p prime in Newton. And thirdly, a degree 2 leftover is solved by a quadratic formula, but a complex root buried in a high degree factor needs a direct complex method, which is exactly Müller's in the next episode. With those in mind, deflation plus Horner is a workhorse you will reach for again and again. Exercise 1. Use synthetic division to evaluate p of x equals x cubed minus 5x squared plus 17x minus 13 at x equals 1. Pause and run the rhythm. The remainder is 0, so x equals 1 is a root and the quotient is x squared minus 4x plus 13. Exercise 2. Solve by deflation. You just deflated that cubic to the quadratic x squared minus 4x plus 13. Find its two roots and notice what kind they are. Pause and apply the quadratic formula. The discriminant is 16 minus 52, which is minus 36 and is negative. So the roots are complex, 2 plus or minus 3 iota. The cubic had one real root and a complex pair, exactly as the fundamental theorem promised. Exercise 3 to test your understanding. You deflate a degree 10 polynomial all the way down one root at a time. Why are the last roots you find the least accurate? And what single habit fixes it? Pause and reason. Each deflation folds the previous root's error into the quotient. So the error compounds. The later the root, the more inherited error it carries. So the fix is to polish every root with Newton on the original polynomial and peel the smallest magnitude roots first. And that's how you hunt down the zeros of a polynomial. Thanks for watching. Horner evaluates p and p prime in one cheap pass each. Newton rides on top to find real roots and deflation peels them off, shrinking the degree every time. Just remember to polish on the original polynomial to beat round off error. But deflation left us staring at a complex pair we couldn't reach from the real line. In next episode, we meet the method that goes straight after it, which is Müller's method, a parabola through 3 points that finds complex roots directly. Like, subscribe and try the exercises before next time. See you there.